Good morning to our attendees. Warm welcome to those joining us from Asia. We are thrilled to have you all with us today for our webinar, SPMI Protocol Analysis Masterclass. My name is Pranav Jagdish and I'll be your host for today's session. We have two esteemed presenters with us today, Mr. Godfrey Coelho and Mr. Anuj Shanbag. Godfrey has over 25 years of experience in the test and measurement industry, and Anuj is a seasoned senior FPGA design engineer with a wealth of experience in designing and validating high-speed protocols. During the webinar, our presenters will share their knowledge and experience on SPMI protocol analysis. We encourage you all to participate actively in the webinar by posting your questions in the Q&A window. The last 10 minutes of the webinar will be devoted to answering your questions. Please note that this webinar will be recorded and a link of the recording will be sent to you after the session. So if you experience any connectivity issues, don't worry about it. You will not miss out on any valuable information. Now, without further ado, I would like to hand over to our first presenter, Godfrey. Over to you, Godfrey.
Yeah, greetings everyone. And so thank you, Pranav, introducing me. So I'll be talking about a couple of slides here. So today's presentation is about SPMI protocol, System Power Management Interface. This is a specifications defined by MIPI Alliance to mainly target for mobile products such as mobile phones and also in automotive application. So in order to do a good design and deploy the product, Prodigy has developed a SPMI protocol exerciser and analyzer. This product has been in the market for quite some time now, and a lot of customers are using it, but we see a more and more interest in the marketplace. We thought of conducting this webinar again so that those who are new joinees, newcomers can understand about SPMI protocol and also how to test that in case when they want to validate it. So we will be presenting about SPMI overview and the major features of it, and also an overview of the protocol basics. And then how does SPMI protocol exerciser and protocol analyzer can be used to validate your designs and also debug it at a different use cases. We have a couple of products. One of them is a SPMI protocol exerciser and protocol analyzer, and second product is a logic analyzer with the SPMI protocol decoding capabilities. And most important is that Anuj is going to talk about challenges in SPMI and how Prodigy is addressing it. And that's overall of the summary of the seminar today. So just to give a glance about Prodigy Technovations, we are now almost 14-year-old company, and we are based out of Bangalore with the distributors in Japan, Korea, China, Taiwan, Southeast Asia, and Italy, Germany, France, Israel. So we are having a lot of sales operations in different locations. We also do direct business with the US customers and also customers who are based out of India. And we have been developing different protocol exercisers and analyzers for low-speed interfaces like I2C, SPMI, I3C, and also high speeds like PCI Express, UFS 4.0, very high speed. We have a two range of product portfolio. One is a protocol analyzer and exerciser, which is a standalone faceless box which interfaces with the Windows-based PC, and then it gives a software GUI which allows you to write all the exerciser script as well as acquire the data and analyze it. And second range of product which runs in the oscilloscopes, we mainly support Tektronix Windows oscilloscope with also decoding capabilities and electrical validation capabilities. So these are the two product portfolios we have been offering over a period of range. We have been covering almost most of the interfaces in the market to do this protocol decoding and analysis. So with that, I think I will now hand it over to Anuj, and Anuj will present about the SPMI protocol exercises and its overview.
Yeah, thank you, Godfrey. So I'll be taking over for this. So welcome everyone to this webinar where I'll be speaking about the basics of System Power Management Interface. So this is a MIPI protocol. And as we progress, I'll explain briefly about what our product is, what it does, what are the challenges it can solve on your end, and a brief live demo about some of the major features that is present in our EXPD. So coming to the basics of the System Power Management Interface, it is a two-wire bidirectional interface. So that means the clock and data pins what is available can be TX and RX both can drive at the same time alternatively. And majorly SPMI is used to dynamically adjust the supply and the substrate voltages inside an SoC. So you have a power controller which can communicate with power management integrated circuits in the system. And this power controllers, we call it as controllers, respectively in the specification. And all this management integrated circuits, we call it target. So in total, the SPMI bus can support up to 4 controllers and up to 16 targets. And the bus voltage of this protocol is 1.2 or 1.8 volt. Now this is a brief diagram. This is taken directly from the SPMI 2.0 specification. So how a SPMI interface looks like. You have multiple SoCs and this has SPMI master. Master refers to a controller and SPMI clears is referred to as targets. So you have a multi-controller and a multi-target bus scenario, which all share a single clock and data line. Now coming to the major features that we have in SPMI, so as I already said, it's a multi-controller and multi-target. So the problem arises is who can take the priority, which controller or target can send the SPMI traffic. So for this, there is a complex bus arbitration process which allocates the SPMI bus between the controller as well as target devices. So there is an extra feature where even the targets can initiate transaction in SPMI. And when you have a multi-controller, need not be that every time the controller has to be available to observe what traffic is happening between different targets and controller. So there is a process where it can connect at any point of time, it can disconnect, or it can just observe the traffic. Now coming to the third point, we have a target initiated communication. So in most of the other serial protocols, you observe the targets are just receivers. They just respond to what commands they are getting and respond with the data. But here we have a separate request capable targets that can initiate SPMI sequences and it can transfer data to other targets or controllers. Now to have a good communication between controllers and targets, you have acknowledgement bit. So whenever a controller sends some write traffic to the target, it can respond with acknowledgement, or if it did not receive the traffic, it can give a NAC. And to identify the different controllers and targets, you have MID and USID. So these are IDs. So in total, you have 2 bit of MID and 4 bit of USID to identify 4 controllers and 16 targets. And to detect errors, if during transfer, if there is an error occurring on the line and the receiver receives a different packet, there is a parity bit to detect. So it detects odd parity in the frame. So there are various parity bits for command, data and address, which I'll be explaining when I go to the frames. And the speed of the bus can be classified into 2 ways. One is low speed and high speed. So the minimum frequency that the SPMI has to transfer is at 32 kilohertz up to 15, and at high speed can go up to the maximum of 26 megahertz. Now coming to the specification, currently SPMI is running at version 2.0. It has a older 1.0 backward compatibility, and there is a optional PICA. So this is protocol implementation compliance. So this is a 1.0 version. So this is used if you want to check if your controller or target is compliant to the SPMI specification. And the major changes with respect to the older SPMI 1.0 specification is the memory map for target is unified, so it's very simpler. And the addition of acknowledgement bit was in the version 2.0. And if there is any parity error occurring while the traffic is happening, how the system has to respond to it. So these conditions were added into the new specification. Now coming to the SPMI sequence, so the bits are sent MSB first, and every sequence, it is initially started with the arbitration process, which I was explaining before, which signifies which controller or target has to get the control of the bus. And after that, you have something called as SSC sequence start condition, and it proceeds with the frames. So what kind of, it can be a write, read, authenticate, different frames are present in SPMI, and it can end with either acknowledgement or a bus park cycle. So in this detail, I'll be explaining in the further slides. So starting from the first, the bus arbitration. So it has a sequence where every controller and target can participate in it, and based on the priority table, it will be allocated to one of the devices. And sequence start condition, it's a very unique condition where clock is held at low and data can toggle from 0 to 1 and 1 to 0. So this is to signify to all the devices on the bus that a new frame is going to begin and they can synchronize to it. So it's really important in a part of the SPMI traffic. And coming to the frames, you have command frame, data frames, and no response frames. So command frame, this is beginning after your sequence start condition. So the first 4 bits is reserved for a slave address, or if this command is being targeted towards a controller, it will be a master ID. So you have 2 bits of MID and 4 bits of SID. So after this, you have 8 bits of command payload bits. So this signifies what type of command it is. There are various command frames which I'll be explaining during the live demo as well as briefly during the slides. And data and address frames are multiple of byte, that is 8 bits. So every byte has a 1 parity bit at the end. So this is an odd parity, so that the entire frame, including the parity bit, should have odd number of ones. And no response frame is if there is some error occurred, or sometimes all the bits including the parity bit, if it is 0, it is called as a no response frame. Now parity bit, as I've already explained, it is odd parity. So the total number of logic 1 bits in that frame should be odd number. And acknowledgement, it consists of 2 cycles. This is at the end of any write sequences. So first cycle is for whether to inform the transmitter whether it's acknowledgement and not acknowledgement, and the second cycle is called as a bus park cycle. So bus park cycle is a unique sequence to make sure that the data line is present in a known state to everyone. So logically, clock and data has to be in a logic low state during idle condition. So at the end of every frame, it is finished with the bus park cycle. So bus park cycle, it starts with whoever is the current target or controller driving the data line, it has to actively bring it into a low condition, and then it has to leave the bus, that is into the high impedance state. So there are pull down resistors on the bus which will take care of it. So bus idle condition is where clock and data has to remain in an idle state. So the clock is always actively driven by something called the bus owner master or is a bus owner controller, and the data will be in a high impedance state where the pull down resistors present on both master and slave end can keep it at a logic low condition. Now coming to the arbitration process. Now the devices which share the bus arbitration procedure take alternatively based on the priority table on who gets the control of the bus. So in this, you have 2 types of method, that is controller and target arbitration. So the highest priority is given to the target arbitration. So targets can participate in the arbitration using one is called A bit, which is the highest priority, and then you have the third priority that is given to the SR bit. And controllers can participate in a priority arbitration or in a secondary arbitration. Now let's take an example of a controller arbitration. So connect sequence is something that I'll explain in the next slide. So any arbitration sequence begins with a controller or a target driving an active high on the line. So before this, the bus was in idle state and the data went to a high state. This is called as an arbitration request. And the bus owner controller will start the clock and it begins the arbitration sequence. because multiple targets and controller can request for arbitration at the same time. So this arbitration sequence is to know who wins the arbitration procedure. So there are different slots available for controller, different slots available for targets to drive active high, and whoever gets the priority will get the controller temporarily, and whoever lost the arbitration can try request for arbitration again after the end of the frame. Now this is an example of target arbitration. You have two methods, A bit and SR bit. So A bit has the highest priority in SPMI arbitration procedure. So once the A bit has been set, the controller gives additional clock cycles where the target can drive its SID, USID, so that everyone knows who is getting the control of the bus. So similar procedure is also followed by SR bit. Now connect sequence. So this method is for if there is a controller that is suddenly become active and he wants to join the bus. So the controller does not know how many bus owner control is there, how many targets are available on the bus. So it requests for arbitration, and in the third clock cycle, which is called as C bit, the controller can drive a high on it, and the bus owner controller will drive its MID. So using this, it has to calculate something called as MPL, master priority level. So this is a round robin thing which keeps on changing every arbitration procedure for controllers. Now coming to the initialization method. So this is when all the masters are waking up on the power on and they have no idea if there is any controller or a bus controller present on the bus. So they request for arbitration, and based on their ID, that is the MID, the lowest MID controller will always get the bus owner control. Now the same procedure is also there for request capable targets. Now this was all related to the controllers. Now coming to the targets cannot drive S clock actively. They can have some pull down resistors on their end which can keep their signal at a logic low. That is all. So, and in targets you have two different types. So one is request capable and one is non-request capable. So request capable can only receive the command sequences, can respond to it, and also it can send the sequences, and non-request capable is just there to respond to whatever it gets. And to arbitrate, it has two methods. One is A bit and SR bit. The register space for a target is from 00 to FFFF. So this is 16-bit address, and it is divided into three subdivisions. You have basic space, you have an extended register space, you have an extended long register space. And this is really important for what type of command sequences you are trying to send to it. So there are some command sequences like write or read which can access only basic space, which can only access extended and extended long. So that is why the subdivision is present. And a target can operate in 4 states: startup, active, sleep, and shutdown. So based on it can be put in a sleep mode if power, it's like a low power mode. It can be active. The active state is the default state where it can transact. It can go to a shutdown state and it can again go back to startup. So startup state is for during power on method. So these are all the command sequences that is present in the SPMI Protocol 2.0. So some of the basic commands is your reset, sleep, shutdown, wake up. So this is related to your target operating state. You have write read commands like this extended register read long. So why this difference is based on what register space you're trying to access. So register write and register read can only access basic register space, and similarly extended long commands can access up to the extended long. Now this was related to the basics of the SPMI protocol. Now I'll be talking briefly about our product, that is PGY SPMI EXPD. What are its major features? How it will be useful for your debugging, for your pre as well as post Falcon validation. Now coming to the major features, we support both 1.0 and 2.0 specification. So you can choose it which you want. You have the ability to configure it as a controller or target. So we have an option where you can add up to 1 controller and you can add up to 3 targets. And there is a unique feature in our SPMI where there is an option of a sole controller. So I was talking continuously about the arbitration procedure. So let's say you have a system where there is only single controller present and multiple targets present. So there is in targets also, if it is non-request capable, so there is no need for arbitration procedure. So there is a unique feature in SPMI where in sole controller method, the arbitration procedure does not have to take place. The frame will directly start from sequence start condition. So we support this features also. So our target can be configured as a request capable or as a non-request capable state. We support the bus arbitration procedure. All the 4 levels of arbitration procedure is supported. You can generate different SPMI traffic, all the command sequences that I showed in the previous slide. And we also have extra features like error injection. So you can insert parity errors to see how it responds. You can ACNAC error, you can put skip SSE errors, and related to the system parameters, you can change the frequency of the traffic, you can change the voltage level. So even though the spec says it is 1.2 and 1.8, if you want to stress test your controller or target, you can try to change the voltage level and even the duty cycle. And we also have an extra thing like you can change the TCO, that is the setup time, if you want to change for your controller and target. And this hardware that we have, it can simultaneously generate SPMI traffic as well as it can protocol decode in the software. So we have a software that will be running on your computer. So this has a continuous communication with our EXPD unit. So as in the picture that is shown here, so this is software that will be running on a host computer. You have that EXPD unit, and this, let's say this example of a DUT, device under test. So we'll be providing the probe cables, the clock data and ground lines, and you can connect this and observe all the protocol traffic in the GUI. And we also have an optional PICS support I had explained to see whether your controller and target is compliant to the SPMI spec. We support that as an optional feature. Now coming to the challenges that we have faced. So these are the most common challenges that most of our customers have reported back to us. And so we decided to put it in a slide. So if you have a similar doubt, it will be easier to understand for you. Many customers have faced the issue of SPMI, the continuous traffic, and they don't know they want to see a particular frame or a particular event happening. So we have an option of advanced trigger where you can set a trigger for, let's say, an extended register write, and you want to see, okay, what was the data sent or what was the address it had tried to access. So you have the option of setting a trigger. And one of the extra features that we have added to our customer was you have something called the hold state machine in target. So once a RCS target request using the A bit, it cannot request again using A bit. It has to request using SR bit. So that is one problem. So we have implemented a hold and clear feature where you can clear all this hold of the A bit or SR bit so that the request capable targets can request again and again at priority traffic. And all the sequences that I had showed, we have supported this, including optional commands. And some of the parameters like duty cycle, that is T-low, T-high period, can be changed. You can change the clock to Q delay, that is TCO. And let's say you have some 3-4 frames that you want to send and you want to add some delay in between it. Let's say 1 millisecond gap, you want to add a 1 second gap. You can do all this configuration using our SPMI EXPD. And we are fully compliant with the 1.0, 2.0 spec. And even the PICS, we have added most of the test cases that is possible for us to test your controller as well as your target. And the error injection method, I have already explained this feature. You can inject parity errors both on the controller as well as on the target side. And we have giving a very fine-tuned probe cables based on the specifications so that it can support the maximum frequency, 26 megahertz, so that it does not cause USB 3.0 cable to your host computer, and we'll be giving you the installation.exe file where you can run our custom GUI. So this will be communicating with the hardware, and it has 3 probes that is coming out. You have the S clock, you have the S data, and as well you have the ground. So this can be connected to your DUT. And while running, you have 4 different configurations how you can use this EXPD. You can either use it as an exerciser. That means we are able to emulate as a controller, we can emulate as a target, and we can communicate with your DUT, or else we can just act as a sniffer. So if you have your own controller and target and you just want to observe what kind of traffic is being communicated between them, you can do that. We also have error injection method, not just parity error. We can introduce glitches in the clock and data lines, and you can see if that is affecting your system. So this is how a typical software looks like. You have the trigger section, timing window. So this is where the plotting. So this is a digital waveform that is being plotted directly from the bus. So whatever clock and data lines is coming into our EXPD, it is oversampled at 400 megahertz, that is 2.5 nanosecond resolution, that is almost 18 to 20 times of what is the actual bus frequency. So at this high speed, it is plotted. You get a bit representation, what kind of command it is, and everything is decoded using a timestamp. So we have a relative timestamp with 2.5 nanosecond resolution. So it gives you brief details about what kind of which slave or which target or which controller it was addressed to, what kind of sequence it was, at what frequency it ran, including the other things like register address, byte count. And if there is any error occurring on this frame, like if I observed here, it will display what kind of error it was. So this I'll explain in detail while going into the live demo. And so these are some of the snippets that I've added related to our software, like the which kind of window it has. So this will be better if I explain in detail while giving the live demo. So we have the trigger option. This is what I was talking about. If you want to set a particular condition where you want to trigger our EXPD, you can do that. And the protocol decode window, we have the timestamp, the command at frequency, and all of this can be sent into a report, and you can offline load those trace files as well. And the PICS is something that I'll be again showing a brief demo about it. And we have support for PDF as well as CSV report. And in the advanced report, you can insert some images. Let's say you added some cursors and measured some frequency or setup time. You can add all these captures into your PDF report, and you can view this later. So this is all related to the presentation. So now I'll directly go to the software. Okay. Now, this is how our software looks like, and I have currently connected to my hardware. So I have a EXPD unit connected using a USB 3.0 cable to my computer. And once it is connected, you can do an established connection. This is just to verify that all the communication is smooth between our software to our hardware. Now, coming after this, initially I had explained we have different modes in which our XSI EXPD can run at. So that can be selected using capabilities method. So initially you can select what kind of version you want to run, whether it's 1.0, whether it's 2.0 specification you want to support. And 2.0, if you select, you have again protocol mode, that is the emulator mode, where you can emulate as a device, it can emulate as a target. You have the PICS mode, so this has a license feature which will be activated. And you have just the analyzer mode. So this is when you want to use our EXPD unit as a sniffer. So you can set the bus voltage at which it has to analyze. And this is the latest feature that we have added. This is a glitch feature where you can add glitches, introduce glitches in HD and SL lines in particular frames. You can target it, like it can be an address command or it can be a random glitch. So let me just select 2.0 protocol mode. And once you have selected it, so this is a trigger window which I'll explain later. So coming to the exerciser view, in the voltage level, we have three different voltages configurations that we support. So in variable voltage, you are allowed to change the bus voltage level from 1 volt to 3.3 in steps of 100 millivolt. So you can set it as 1, 1.1 volt, 1.2, 1.3 like that. But the drawback of this feature is that you can only go up to 13 to 14 megahertz at max. So if you want to use our EXPD to the maximum possible frequency at 26 megahertz, you have to use the fixed voltages. So that is 1.8 and 1.2. That is what is told in the specification. So I'll use initial variable to show all the features. Now coming to the device setup, you can either master as in controller, or you can add a target that is a slave. So interface refers to whether it's internal to our board or external. So if you are connecting your DUT, you have to refer it to as external. So it is internal controller that I'm adding. And termination refers to we have a 2.2K pull down resistor on our board. If you have your own pull down resistors on your side, you can disable this, or you can just keep it open. And master mode, this I told whether it is a sole controller bus or a multi-controller. If you select the sole controller, arbitration process is not executed. Directly the frame will start from SSC. If it is a multiple controller, you have to say what is the MID of the controller, and you can add it. So it has successfully added. Now I will add a target. So most of the parameters remain same apart from USID, and you have something called as group ID. So multiple targets can be combined into single group ID. And what kind of address space it supports. So we had three address space: basic, extended, long. If your target is supporting only the basic space, you can select that. And these are something extra parameters if you want to configure. And if you select this as a sole and multiple, a sole mode refers to our target will act as only non-request capable tree. And if it is multiple, it can act as a request capable target also. So I've added one target. I'll add one more target. I'll keep rest of the parameters same. I'll just change the USID. So now if I check in this node network, I have one controller with MID 0. I have two targets with MID 5, USID 5 and USID 6. So all of this can be saved. So every time you don't have to manually do this, you can save this configuration and load the configuration again. Now, once the configuration is done, now you have enabled it, you have to click on Start Capture. So now our EXPD is actively trying to find SPMI traffic on the bus. So we have a oversampler at 400 megahertz, which is trying to find the sequence for request for arbitration or SSC condition. Now to generate the traffic on the bus, you have script window, or else you have the option of the UI window. So I'll explain the scripting window, which is more simpler. You have one for master as one for slave. So in master, we have different kind of scripts. So these scripts can be triggered using a space. So you have something called as a sys script. So here you can change all the system parameters related to the exerciser. So you can set the frequency. So this is in terms of kilohertz. So that means it is 10 megahertz. I can set whatever voltage I want. I'll take the default of 1.8. Let me check. And TCO is the setup time from the driving edge, what gap has to be given when the data is outputted. Let me initially keep it as a 0 so that I can show later one by one. So duty cycle is the of the clock. You have three options: 25%, 50%, and 75%. And TIMJ refers to the gap between the frames. So this is the system command, we call it. So this is related to all the system parameters of the board that you can set. So it need not be one at a time. You can send multiple scripts at the same time. Now, since I had selected multiple controller bus, so I have to initialize my bus, and you have methods, method 1, method 2, method 3 on how the controller has to connect to the bus. So I'll select the basic method 1. And now the bus is trying to initialize, but it does not have any traffic. So let me send one of the commands. So let's say register write. I already have a target which has the SID of 5. and immediately you can observe that the traffic was sent and it was captured back again. So it is very quick, and all of this traffic is being directly stored in your host PC. So we don't have any buffering or delay between when you generate the traffic and when you capture. So the limitation for capturing maximum amount of time is completely dependent on your host PC. So this is the traffic that was generated. So since this was the initialization, it took 96 microseconds. And you have the arbitration sequence, you have the priority arbitration, you had the SSC, so the entire frame is sent. So let me send multiple commands like this. So I have a lot of saved scripts. So all of these scripts will provide you this basic templates. You can edit this and you can save it back again. You can edit this in a notepad or a text file. So I have multiple scripts saved here, which includes a lot of write, read. I'm trying to access basic address space, extended register space. I'm trying to force the controller target to go into a sleep and wake up method also. So now you have all this traffic that is captured. Now just to give a brief of how everything works in this UI. So coming to the plot view, you have the clock data line and the bus representation. So this gives you a detailed view of what was C bit, what was A bit, what was the command value, what was the address, what was the data value, and if error anything occurred. And if you see in writes, you have the acknowledgement bit as extra, and you can zoom out, you can use your mouse to scroll in, scroll out, you have a pan, as well as you can set some cursor. So let's say you are trying to measure some setup or hold time, or let's say you're trying to measure your width, your high period or low period of the clock. So you can place cursors and you can measure all this, and you can capture this image. You can capture all these images, and let me say, and these images can be added later into when you're generating the report. So that is one of the good features that we have, and you can fit this frame and you get a bit representation. So for each sampling edge, what was the bit value that we had received, that is related to the plot view. Now coming to the decoded result, you have the serial numbers, you have the timestamp. So this is a relative timestamp based on which we calculate. You have the slave ID, if you have the controller ID or target ID, what kind of command was sent, at what frequency, and the register address, what was the data. You can even see what data was sent. So this is 1 byte of data. So if I open this, so you have the data that was sent even during write as well as read, and if any error has occurred. So if there is any parity error occurring, it will be displayed. Now that is related to the decoded results. Now I'll show you some of the features that I was talking about. Mainly I can start with system command. So as I already told, now the frequency can be changed. So let me change it to something else. I was sending at 10 megahertz, so let it make it 1 megahertz. I can change the voltage. So let me set some TCO value. Let me add a TCO. It's in terms of nanosecond, and duty cycle, let me keep it as constant. So just to give a reference of how it would be. So this was the traffic that was sent, and the TCO refers to the data has to be driven on the rising edge of the clock. So this is the gap that was generated. So it's a 20 nanoseconds. So I can generate up to the maximum high period of the clock. And I can set this as 0 and try to change the duty cycle. So this is 25% duty cycle clock. I can make it 75. So we have 3 options, or I can keep it as a default. And so this is the default what we have. And let me say I want to add some gap in between 2 frames. So let me take a register write and register read. So I'll just clear this window. It will be still saved in your tree file. I'm just clearing the window so it's easier. And I've added a 1 millisecond gap here. So I can give it terms of microseconds, milliseconds, and seconds. So here only you can observe in the timestamp that 1 millisecond gap was there between 2 frames. So this is useful when you want to add some delay in between the frames. And coming to the error scenarios, you have command parity insertion, data parity insertion, as well as address parity insertion. So let me take an example of extended register write, and I'm trying to insert some command parity. So it's observed in the decode result that command parity error came. And since it was a parity error, even the slave responded with a NAC. So how the error has occurred is, as I told, it's an odd parity. So even though there was a single bit, the parity bit should have been a 0, but it came as a 1. So similarly, I can insert error in data. So this is data parity error which is being displayed, and I can even insert parity error in address. So this is most of the features that we have. We also have a loop feature. So let's say you want to send a single command in a continuous loop. You can try to do that as well. So let me take an example of a register write, and let's say I want to loop this 10 times, and I can change the frequency for each script. So let me start with 1 megahertz, and for every script it has to increment by 1 megahertz. So if I clear it again, so in total 10 times the script has to be sent, so 0 to 10, and for every frame if you observe, it is keep on incrementing by 1 megahertz. So this is also another feature that we have. So this is related to the controller. Now coming to the target, so I had configured my target as a multi-controller target scenario. So it can also initiate the SPMI transaction. So I had already told you have two ways. One is A bit and SR bit, and A bit has the highest priority. So from this is slave target number 5 and trying to access target number 6. I'm trying to send a similar command register write. So if you observe here now, this was the previous frames where you had observed that no other device or controllers were trying to participate in the arbitration. But in the current frame, you have the A bit set and you have the target ID coming. So it won the arbitration and it got a chance to send the SPMI traffic. So similarly, you can send it using SR bit. So the same will follow for SR bit. And we have the extra feature of a register access. So let's say your target is a read-only registers you have, and you want to emulate that in our side. So you don't want to send any write command. So you want to directly want some value to be stored in our register. So let's say in register number 1, I want to store these many values. So it will be register number 1, 2, 3, 4. So I can directly write all of this value into my register space of my target. And in master, I can directly, if I try to access this register, so I'll directly do a register read of that. You will see that. So in the target side, if you see for register number 1, I had inputted a data 20. So when I'm trying to read it from my controller side, the data is already present. So this is useful when you wanted some preloaded data already present in a register space. So you also have a feature of search and filter if you want to search some values, like the register write. If I enter, it will show you that 12 amount of commands were observed. You can reset this, you can filter in, filter out, and you have also the report feature. So if I quickly show you directly the advanced report, so since I had captured my images and I just click on generate, and if I just replace this, so hopefully this is visible. So in this PDF file, you have the device list, how many controllers and targets were added. And in the protocol list, you have what are the frames were sent and the images added to it. So this is that. That is all related to the controller and device side. So this is what's related to protocol mode. So similarly, you have the analyzer mode where you can just capture the traffic. So let me just show you the glitch generator. So let me try to generate some glitches in HDA line and let it be randomly. And the glitch width let it be 10 nanoseconds. And so from the device, if I just clear this, And if I try to send some scripts, you can observe this glitches being generated. So if you check the width of it, so we can similarly generate glitch as well as in block line. So that is a little bit critical because it will affect the decoding. So this is randomly generated. It can come in address, it can come in data, it can come in command. So all of these options are there. Now that is related to the protocol mode. Now quickly let me just show you how a simple trigger works. So then I'll move into the PICS mode. And so I have an option of, let's say, register, extended register write. I want to trigger with slave ID 5, and I'll set a trigger. So you have to stop capture and start capture for it to reflect. So if you see observed here, a T was observed here, and same thing is being reflected here. So this is how it works. So, and everything will be negative because that is the zeroth location for us. So you can set a particular trigger, and you can even go to the trigger positions if you have multiple frames. So that is easier. And you have, this is a simple trigger where only one level of condition you can put. In advanced, you can set a sequence of conditions where extend register, read, something like that. So this is all related to the trigger. Now I'll show you briefly about the PICS mode of how it works. And one more feature I forgot to mention is the reset all. So many of our users had reported that they are not physically present while accessing our hardware. So they'll be doing work from home or remote accessing it. And to reset the board or power off on, it's very difficult. So we have an option where you can remote reset your hardware directly. You don't have to be physically press the board reset what we have on our board. So it will reset the entire fabric. Now you have to establish connection again because the reset was sent. Now let me start with freshly with PICS mode. So PICS mode is available only in 2.0 specification, and you can choose here what kind of test you want to do, whether you want to test your controller, whether you want to test your target, whether it's a request capable, non-request capable. And the configuration remains same as protocol mode. You can choose how many devices we have to add to test it. So in this scenario, since I have a single board setup, I'll add my own controller, and let's say I'm adding 2 targets with IDs 5 and 6. So in total, I have 1 controller and 2 targets, same configuration as protocol mode. And once configuration done is pressed, you get all these test cases. So this is all related to the PICS document. So whatever number that you see, VA0, V3 for an example, you can directly go to your PICS document and find this test case, and it will give you a description of what it is. So 1 sec. So I had selected a controller. I had actually wanted to select the device. So just let me re-add it. So these are all the test cases. So we have separated the test cases for a controller and target. And whatever scripts that I initially showed, sys scripts to change voltage frequencies, we have given it as an input. So still you can change at what frequency you want to run this test cases, at what voltage, to which target you want to test. So all of this is possible. And so let me just select all the test cases and just click on send. So it ran all the test cases. So if you see in green, that means the test case is passed, and there is one failed. So this is because we don't have a non-request capable target present. So that's why the test case is passed. And based on that, you will have the corresponding, you can see what test cases the frames were sent for it. So you can either select individually or you can select all and run it. And the same thing, you can generate a quick report. And the report gives you the device list. and what are the results of the test cases. So for test cases, what was whether it was a controller or a target that was under test, and whether it was a pass or fail. So we'll get this under report. So that is related to the PICS protocol. So if you have any queries, do drop your queries in the Q&A section. So that's all from my side. Thank you. So I think Godfrey, you can take over.
Yeah, there are some queries, Anuj, like the first one is, what is a skip SSC error? That maybe you can answer that. What is skip SSC error?
Yeah, so the skip SSC is if you want to send a frame without the SSC present. So it will just be an arbitration sequence and will just start with the command and ID. So if you want to, so that is one of the errors that we can use.
Okay. Second one is, what is the maximum amount of data that can be sent through the unit?
So individual commands, there is a limitation based on the type of command. So extended register write and write long has its own byte count present inside the frame. So it lets say 16 bytes of data maximum it can send. But if you're talking about in the entire script, like if multiple scripts, if you have, we have a 16K depth of buffer inside. So if you can send like 100 scripts or 200 scripts, and this also can be continuously streamed. It doesn't have to be just in GUI, you can send it through API as well. So it is, we have a limitation of maximum 255 scripts at a time, but in individual frames, it is related to the protocol, how many max you can send.
Yeah, I think I also like to add that, like those who want to do a complete automation, they can use API using Python scripting, and Python scripting is supported for the product, and we can provide you a support on that. So the third question, how do you connect Prodigy unit to the SPMI bus? Okay, let me take this question. So we provide a flying lead set connector, other end of the cable, one end of the cable as a connector, which will mate with the SPMI exerciser and protocol analyzer, and other end as a female connector, work post connector, which is around, I think, 2 millimeter in size, which we can insert to the header pins on your DVT. There are 3 connect points: clock, signal, and ground. And these cables are specialized cables to handle the maximum clock speed of, I think, 26 megahertz. So that's the full support we are providing. So these are the few questions we had. Any more questions? Please feel free to add. Okay, there is one more question now. In analysis mode where pass-fail report is produced, is there a way to see the edge timing of the pass-fail? Yeah, well, I think in the GUI you can do that. Like, no, you can select that frame, and you can go and see maybe place the cursor where it exactly failed. But we are not pinpointing the timing. Like, no, we really not going to the details of it. We're just analyzing, but you will know which frame it is, and then you can go and debug that further. Yeah. So any more questions? I think there was some questions. Someone was raising hand.
Yes, Godfrey.
Okay.
Yes, Godfrey, we have a few more questions.
Yeah, go ahead,
Yeah. So one of the questions is, what is the difference between SPMI 1.0 and 2.0? And does Prodigy's analyzer support them?
Yeah.
Anuj, can you take that? Yeah.
Yeah, sure. So we support both 1.0, 2.0. 1.0 is completely backward compatible. You can choose both of them. The only difference majorly in frame-wise was the acknowledgement bit that was added in 2.0. Internally to protocol, a unified map was added. But we do support But at a time, yeah, either it can be a 1.0 bus or it can be a 2.0 bus.
Okay, there is a one more question here. Minimum transfers
Thank you,
gap
Anuj.
can.
There is one
Pranav,
more question.
Pranav, can I take this question? Yeah. Minimum transfer gap can be. I think we are. I think it's talking about between the two commands. What is the gap?
Correct.
Yeah.
So in default, I think without setting anything, it's 80 nanosecond or less or something gap. But using the TIMG parameters right now, it's 1 microsecond what you can set. That is the minimum you can enter.
Okay. Okay. The next question is that slave indicates. Will you please give an example? It's not clear to me what this question means, but if we can interpret, it will be good. Any idea, Anuj, what this question could be? Slave indicates. Yeah.
They're asking what do you mean by a slave. So these are, I think, power management integrated circuits, what we call it, PMIC. So we call it either slave or we call it as a target on SPMI.
Yeah, the current terminology used by MIPI Alliance is target and controller. Host is known as controller and slave is known as a target. So that's the terminology we'll be using it going forward. Yeah. I think there is someone raised hands. I request them to post a question.
Yes, there is one more question.
Yeah.
So does the Prodigy exerciser support 1.2, 1.8 and 3.3 volts?
Yeah. So we have the 3 modes that are EXPD. So if you want to run your SPMI bus at the maximum frequency, that is 26, you can run it at 1.8 or 1.2. So those are the only 2 voltage options. If you want to run it at any other voltage, take an example of 3.3 or 2.5, the maximum support that we have is 12 or 13 megahertz at most.
Yeah, we can have a variable also where user can keep vary the voltage in the steps of something around 50 millivolt also. Yeah, up to 15 megahertz. There's some more questions I can see. What is the response if we get command parity from the master and slave?
Yeah. So if slave receives a parity error, it usually ignores that command sequence. So it will, if it is a write, it will respond with a NAC. So if master is observing any parity error occurring and it was not the transmitter, it has multiple options. So if you go through the PICS document, you have different methods for how to respond to a command parity, how to respond to address parity. So for a command parity, it will actually stop the clock and it will restart again to inform that the frame has been terminated, or it can just ignore the sequence, or it has other methods where when it transmitted and parity error occur, it can disconnect from the bus and try to connect back again. So there are various options for it. You can, if you want, we can share you, like in the PSS document, if you can go through our specification, you will get much in-depth answer for it.
Okay, the next question is, what is the difference between protocol mode and PICs? It seems you can simulate same things.
Yeah. So protocol mode, you have to manually type all the frames that you have to do, including if you want to change the frequency or if you want to test something, you have to manually type all the scripts. We do give sample scripts, but modification has to be done by the user. So in PSS, what we have done is we have taken the test cases from the official PSS document and we have written our own test cases for it. So let's say if it has to be like measure the maximum data bytes that can be sent. So we test it manually, sending multiple scripts at a time to test one test case. So we have put efforts into differentiating controller test cases, target test cases. Even for target, we have request capable and route request capable. And we have manually inputted all our scripts. So it will be easier. So you just have to select the test case and run it, and it will immediately give you a pass or fail. But But if you had to manually do it, you would need some expertise on it and would take you some.
Okay, so let me add some more information. PIC stands for Protocol Implementation Conformance Suite, I think. This is given by MIPI Alliance SPMI working group, which basically running those test cases for a controller or a master or a target or a slave. User can make sure that the interoperability between different devices can be achieved much more confidently. So that's a few of the readily available test cases, which we have implemented in our SPMI exerciser and protocol analyzer, and offering it as an optional feature to the user, so they can have this as a ready-made test cases and running. The protocol mode, you can write your own test cases as per your requirement. It gives you full flexibility into writing different test cases. That's one of the difference also. The next question we have here is that, can you send the slides and demo at the end? Yes. We will share the slide deck and demo. We have recorded this session. This recorded session will be shared with all the attendees as well as those who have participated in this, registered for this event. Yeah. So these are the questions we have at this time, and I think we are almost done with the time. Pranav, over to you.
Yes, thank you, Godfrey and Anuj, for this very informative session. And thank you all to all the participants for joining. You can always visit us at www.prodigytechno.com for more information, or you can email us at contact@prodigytechno.com for any information that you would require. Thank you all.